Report. Okay. Yeah. So what you see, so there are three things I want to cover today. The first one is the syllabus, and then the basics of instrumentation. And the third one is the linear regression. So I am the instructor and coordinator of this course, and I'll be teaching it with three of my colleagues here. And I'll tell you in a minute how the breakdown of the instructions are going to be. You have two TAs who run the labs, and this particular syllabus is for the lecture times that is on Thursdays. So every Thursday, unless I say otherwise, we will have a class just like now, from 5 to 6:15. It's going to be virtual through Zoom in the same way that you connected to it. On top of that, there's a Thursday 4 to 5 p.m. office hours, so starting from next week. Or if you have, I'll be available no matter what via Zoom. And if you have any questions, you can email me or text me or email me for another appointment. This course doesn't have a textbook. The materials of that are collected from multiple sources, and the lecture notes will be shared with you, although I strongly encourage you to take notes with as I discuss it with you, as I re-lecture. What you will see in this course, basically in the context of 6 different labs, there will be 6 different labs, 2 materials and structures, 2 dynamics and controls, and 2 aerodynamics and propulsion labs. You will see basics of instrumentation, measurements, linear regression, uncertainty analysis, Fourier transform, and a lot of other things that are related to measurements. So this course is really very, very different from all other courses you have been taught so far. So, and the main reason for that is because in all your other courses, you were given an equation, and here we want to see where those equations are coming from. Also, this is one of the courses that will gauge your performance to analyze the data and to present the data. Because as a result of this 6 labs, you will turn in 2 reports, 2 lab reports, and 4 lab worksheets. I'll explain them in a minute. That comes up to a total of 80% of the total grade. The other 20% is the quizzes. So the first quiz will be next week, Thursday, at the beginning of the class via eCampus. So basically, all you need to do is take a picture of you. I'll share the exam with you via eCampus, and I'll give you instructions where to find the exams. You will upload your solutions in eCampus as well. These are the titles, the items we will cover in this course. I'll leave it to you to read it. This is a tentative timeline of the course. You see 2 lines, 2 columns. One is which you are actually here. This column belongs to your sections because you are on Thursday classes. And this column is for Tuesday classes. You see 2 columns here, the lecture period and the lab period. So the first 3 weeks is going to be primarily lectures so that you come up to speed so that you can run the experiments. The format of the labs are going to be virtual because we cannot do social distancing with the number of equipment we have. So the way it will work is that the TA will share with you the labs, the videos of the labs, I'll give you lectures of the labs. The TAs will give you videos of the labs as they're running it. They give you pre-recorded video. They give you lab manual, and they give you raw data, and you have to basically turn in the lab reports or worksheets. So format of the quizzes is going to be via eCampus. So as I mentioned earlier, 2 of the labs, and I'll be explicit when we have the labs, will be via groups. We will put you in groups of 3 or 4. You can communicate with each other via eCampus, via Zoom, or you can meet with each other if you can follow the social distancing groups. And every group will turn in 1 lab report for those 2 labs that have a lab report. The other 4 labs will have a lab worksheet, which is a condensed version of the lab report. It's not as elaborate, and so you will turn it in individually for each lab sheet. I'll be very explicit so that you guys know exactly what you need to do for each lab. The ABET, which evaluates student performance outcome, the details are here. I'm not going to go through it. If you have any questions, let me know. So before I move on to the next item, any questions on the syllabus? Please unmute yourself if you have questions. Questions? Okay, good. So now let me share one more thing with you. When you go to eCampus, you should see something like this. If you go to course materials, you should see 3 items here. Is there anyone who doesn't see these 3 items on their eCampus? Please take a minute and look at your eCampus, your own section, and see if you see these 3. The first one is the syllabus that I just went through. The other 2 are 2 folders. The lecture videos is an empty folder. The lecture materials has 2 items in it, 2 PDF files in it. So just look at your eCampus, and if you don't see it, let me know. I give you another 30 seconds to check that. Good, excellent. I am hearing from 2 of you that it's good. 3rd person, just a few more people. Okay. Good. Okay. Thank you, folks. You don't need to send the message anymore. If some of you can see it, all of you should be able to see it. Good. If there's anyone who doesn't see it, email me after the class. And then we have to figure out why and fix it. Okay. So now what I'm going to do is, in the lecture materials, I will open the basic concepts, okay? And which I have it open, so let me just go directly to that. This is the basic concepts, okay. This is the basic concepts of aerospace, the lab course. And so these are the names of the instructors. So let's start by discussing, if I find my, okay. I want to start by discussing why we're doing what we're doing. Why do we do experiments? So the question we want to ask is, why do we need to do experiments? And in order to answer that question, let me ask you a few things, and I will be very happy if a few of you can unmute yourselves and speak out what you remember from these equations. What is this equation?
Bernoulli's.
Exactly. So basically, this is saying that if you increase the velocity of a fluid, the pressure goes down, something like that. Okay. So Bernoulli equation. So there was another equation that is, for instance, sigma is equal to E times epsilon. What was that?
Stress strain.
Exactly. This is a strain, this is a stress, and this is elastic modulus. There was another one. L is CL QS. What is L? What is CL? What is Q? What is S?
Lift, coefficient of lift.
Dynamic
Coefficient of
pressure.
lift. What is
Dynamic
Q?
pressure.
Dynamic pressure. Excellent. And S?
Area.
Surface area of the wing. Okay. So now the question is, where did they come from and why do we need them? Okay. I will ask the second question first. Why? And if you really want to know why we need these equations, the answer comes out to be one word: predict. We want to be able to predict the performance of a structure so that we know if it functions the way we want it or not, or if it fails. Now, fail may mean different things. It could be a structural failure. It could be very low range, very low endurance, and any of those things. So if we have a structure, we want to be able to predict where it fails. And the other thing is we want to be able to model a structure, such as in this case, an airplane, to see if a structure that we have in mind performs in a way that we really want it to perform. And if it doesn't, then we have to redesign the structure. But for us to be able to make predictions about the performance of the structure, we need to have equations like this, equations like that, and all of these. So these equations are essential to designing any structure. Basically, these are the essence of engineering. These are the backbones of any engineering. However, the problem is, or the other question is, okay, where do they come from? And the answer to where do they come from is literally the experiments. Okay, so we need to do experiments in order to know where these, in order to discover these equations. Okay, so now, let me give you one example from a structures that is I'm more familiar with. Imagine I am dealing with imagine this is a part of a structure. This is a bar that is experiencing a torque that I call T. And so what I want to do is I want to know what material this should be made of. And let's say I have two choices of materials here. I call it one material A that has a density of 2.7. Oops. Density of 2.7. And another one, material B, this is relative to water, 8.05, and this guy has a shear strength of, let's say, 100 megapascal, And this guy has a shear strength of 300 megapascal. And so the question we want to ask is, which of them is better? And let's say our design criteria is to minimize the mass of this guy. Okay, so our design criteria is to minimize the mass of this guy, and let's say the length of this guy is L, the radius of this guy is R. Oops. The radius of this guy is R. And so we want to see which of these two materials is a better choice for us. And by the way, this is a type of problem that you will see you have seen in 214. So this is the type of problem you have seen in 214. So the first thing I start from is the equation we had in 214, that the maximum shear in this material is proportional to the moment times the radius of the bar divided by J. Who remembers what J was?
The moment of inertia?
Exactly, but the polar moment of inertia. And what is the equation for that? J is equal to what? J was equal to pi over 2 times r to the power of 4. Okay, so if I combine these two equations, what I get is that tau is going to be equal to m, 2 times m divided by pi r to the power of 3. Okay. Now, this for the cylinder to survive, this has to be less than or equal to tau max, the maximum tau that the material can take, the strength of the material, divided by a safety factor n. Okay, so where does that safety factor come from? If the tau max of a material is 100 megapascal, I put a safety factor which is a non-dimensionalized number. It's more than 1. Let's say 1.3 or 1.4. And all it does is that it artificially reduces the maximum stress that we allow in the material. This is to account for any uncertainty that is in material properties or geometry and all that. Okay, so in the limit, I can set them equal to each other, and I can say 2m over pi r cubed is equal to tau max divided by n. Now, there's another thing I know, which is the other thing I know is that the mass of my cylinder that I'm trying to minimize is pi times pi r squared times L times density. This is just the product of the volume, which is these three terms, times mass density. Does everyone agree with me so far? Okay, so then from here, I can calculate R in terms of the mass, and I can say R is equal to m over pi L rho. And the next thing is just very simple, and all I need to do is to put this in this equation, and if I do that, what I get is tau max divided by n is equal to is equal to 2m times square root of pi L to the power of 3 rho to the power of 3 divided by m to the power of 3. So, and I can rewrite this equation to get m. M is the one I'm trying to minimize. And if I do that, m will be a very nice equation that is 2 times n m to the power of 2 over 3 times, that is 2 over 3, times pi to the power of 1 over 3 times L times rho divided by tau max 2 over 3, okay? So if you look at the three equations, we have 3 parts of the equation we have. This term is about applied load. This term is about geometry. So this is about load. This is about geometry. And this is about what? What is this about?
Material.
Material.
Exactly. It's only material. So basically, if I want to compare the two materials, all I need to do is compare these two terms between the two materials, okay? And if I do that, and I go back to my first slide, so basically I need to say what I need to calculate is rho over tau to the power of 2 over 3. And for this material, it becomes 0.12. And for this material, it becomes 0.18. Therefore, which one is better, A or B? Which one gives me lower mass? Let me go back in here. Look at it. And now here, which one? Good. A is a better material in this case. Now, a tricky question. What material is A? What is B? Who knows that?
Is it aluminum and steel?
Aluminum.
Yeah.
Good. Excellent. Aluminum and steel. And look at here. The strength of this guy is 3 times the strength of this guy. And but the mass of this, or the density of this guy, is less than 3 times this guy. However, because we have this 2 to the power of 3, it means density is more important than tau here. When we do the actual math, we realize that this guy is better than this guy. Okay. And now, why did I show you all these calculations? The main reason I showed you all these calculations is to tell you that if I didn't have this equation, if I didn't have this equation, if I didn't have this equation, I would not be able to say, without making anything, just by doing the calculation, which is much less costly than making the actual part, to say which one will work better. Okay, and so especially this is important because when you look at this case, you see that in terms of lower mass, this has lower mass, but in terms of strength, this guy is higher. So which one is better? Which trade-off? The balance tips towards A or B. Unless we have equations like this, like what you see here and here and here, we will be lost. Okay, so that is basically the importance of these equations. Okay, so now let's continue to this slide. So why do we do it? Why do we do experiments? Well, the answer is simple. We do experiments to discover these equations. That's the purpose of the equations. Now, when we do experiments, we often enter into a cycle which we call scientific method. Okay? And the scientific method, in one way or the other, consists of 4 parts. Okay? And this is an infinite loop, if you look at it. It goes forever. Okay? But you just need somewhere to start, and you start with an observation. So, for instance, observation could be that lift is proportional to velocity to the power of 2. This could be an observation. Okay? This could be, so basically it's, and the way we put it here is we put it as a hypothesis. That's why we call it the prediction. It's a falsifiable hypothesis. That's very important. So basically, based on an observation, we come up with a hypothesis. And the most important thing about hypothesis is that it has to be falsifiable. Okay? And what does falsifiable means? It means the opposite of that is also meaningful. For instance, lift is proportional to u squared is falsifiable because the opposite of that is lift doesn't scale with u to the power of 2. I'm not giving any weight to any of them. I'm just saying these 2 hypotheses, one of them is true, but both of them are falsifiable. Okay? And based on this prediction that the hypothesis can make, then we move on to here to design the experiment. And the way we design the experiment is that we want our input change. We want an experiment in which we can change the input, in this case, velocity, and an experiment in which we can also measure the lift such that all other parameters that may affect lift are constant. Does that make sense? So my control variable, so the variable that I'm changing is u. Everything else is constant, and I'll measure so that allows me to measure the dependence of lift on u. Then I run the experiment. I go to this cycle. I measure the data, and the last part of it is interpretation. Now, the reason it can continue is because maybe your hypothesis will be false. Then you have to continue that. Or the other reason it can continue is that you want now to build a higher order model. You want to make a more elaborate model. Like, let's say you discovered the relationship between L and U. Now you want to see, is there a relationship between lift and dynamic pressure, lift and surface area of the wing, for instance. Okay? And so, in some other words, these are presented here as well, which I encourage you to read them. So the scientific method starts up with an observation. You come up with hypotheses that are falsifiable, which means you make predictions. You say L scales with u to the power of 2 in a linear fashion. Then you design the experiment, you collect the data, and you interpret it in a way that it refutes, it nullifies, or it validates your model. Any questions so far? Okay. And so basically, an experiment is a controlled observation, and what it means is that in most cases, only one variable is changing. For instance, if I am identifying the relationship between lift, and my hypothesis is that this relationship is valid, I control it by keeping, for instance, this constant and changing this and measuring this. So it's controlled. This guy will remain fixed. And I do measurements of L, and I'm changing Q, and I'm answering I am answering a specific question. And the specific question is this thing here. Is this true or not? So we have an output, and the output in this case will be the lift that we will measure here. Now, there are three types of experiments that or you can put experiments in three different categories: exploratory, quantifying, and validating. In all cases, this definition of experiment applies. So let's look at the exploratory experiments. So the exploratory experiment, another word that you can really put that's equivalent to that is a rudimentary experiment. Okay, so if I go back to the experiment that I was telling you, okay, if I want to check this guy, basically at the very beginning, if I have no information about this relationship between lift and dynamic pressure and surface area, one experiment I can do is I can just change the pressure or change the velocity and see if the lift is changing. It will be very rudimentary. I may not do highly quantitative measurements, but it just shows me the outcome of an exploratory experiment is that you get some feeling about what your output depends on in this case. So the exploratory experiment is not the end of the story, it's the beginning of the story. It's the experiment that allows you to design your real experiments, okay? So basically, it allows you to identify the inputs and outputs. And it allows you to ask clear questions, allows you to form your hypothesis, and your hypothesis which should be falsifiable. Now, the second type of experiment that, oops, sorry. Let's first look at the quantification experiments, and then I will go back and look at validation experiments. Let's say I have this relationship between shear stress and shear strain, okay? Basically, I know that if I change shear stress, shear strain scales linearly with that, okay? But if I want to use that as a basis for design of my structure, I still need to know this. So I need to know what this is. I need to know what this guy is, the shear modulus is. So the experiment I do for this guy is an experiment to quantify this value. So that's why we call it a quantification experiment. Okay, and so for instance, in this type of experiment, you say this is your this is your input, this is your output, and what you're going to do is you're going to, let's say, plot, oops, what you're going to do is you're going to plot gamma as a function of tau. And you're going to fit a line to this, and the slope of this line will be your shear modulus. Okay? So that's basically, that's the quantification experiment. This, for instance, in this case, was after, through an exploratory experiment, we identified that the shear modulus and shear strain and shear stress scale linearly with each other. Now, the last type of experiment is validation experiments. Okay? To explain the validation experiment, let me bring one blank page here. Okay. So the first, okay, validation experiments. So for instance, from 201, course 201, with the non-dimensional analysis that you did, I hope you started with something like this. You said the lift is a function of air velocity, density of the air, viscosity, surface area, and some parameter we called A, like the aspect ratio of the wing or the shape of the, actually angle of attack. From here, when you did the non-dimensional analysis, you realized that actually you can write L as this. Which CL has in it, CL is the lift coefficient, which is a function of alpha, is a function of Mach number and shape of the wing, and so on and so forth. So basically, so now what we want to do here, we want to design an experiment to validate this relationship. Basically, what we want to say is that for a given shape of a wing, whether the size is this or the size is this. Oh my God. Okay, whether the shape size is this or the size is this. Oh my God. Okay. The relationship between L and surface area and dynamic pressure will be like this. So basically, this is our hypothesis. That's why I put a question mark there. And if I want to validate that experiment, one thing I can do is I can, for instance, design an experiment. I can design an experiment in which I change the surface area. So basically, and so L was Q, S, CL. I change the surface area, but I keep CL the same. So angle of attack is not changing. The size is changing, but the shape is not changing. The airfoil is not changing. And I measure lift, and let's say I also keep this guy constant. I also keep Q constant. If this relationship is valid, the relationship between L and S has to be something like this. It has to be a line, because my model predicts that. So by doing this measurement and seeing if the individual data points are sufficiently close to a line, I can validate this model and I can refute this model. But that's just one of the experiments I have to do. Let's say this was for the case of U1. I can also do another experiment for U2, where U2 is less than U1 velocity. I should also get another curve like that. If all of these happens, then my relationship is validated. Okay? And if the relationship is validated, I can also use it as a quantification experiment, because when I have the value of L, when I have the value of S, when I have these slopes, then I can also have CL. Because Q times CL is this slope, because this slope is the ratio of L over S. So I can also use it as a quantification experiment. Okay? But, so one thing that you saw a few times today is, which is very, very extremely super important, is this linear relationship. This linear relationship was between L and S, but you also saw it between stress and strain and all that. And all of those are the subject of the next lecture, or not the next lecture, the next topic that we're going to cover today, which is the concept of linear regression. Basically, we want to know how do I find the best line that fits the data? Okay, so now I want to move on to the next handout that I gave you. Please open it, open your next new handout, and I give you 2 minutes break, okay? Just 2 minutes. Okay, guys, are you back? Everyone? Oh, wait a second. Good. Okay, thank you. Let's start. So, okay. So basically, if you think about this relationship or this relationship, these are linear relationships between some parameters. So if I, for instance, in one experiment, I measure stress and strain, and let's say I get some data like this, what is the right procedure to fit a straight line to this? And what would be the slope of, how can I quantitatively measure, how can I measure the slope of this line? What type of equations would I use for that? Okay, so these all and many other problems fall in this category, that I have an dependent variable y, like this here, which is a function. what happened? Which is proportional to my independent variable. Let's just assume that there's a bias 2, okay? And so the question we are asking is, if I measure x, if I change x and I measure y, and I give you this data points, these data points, how do you fit a line to this so that the slope of this line will be a and here will be b? When x is equal to 0, the value of y is b. What is the right mathematical procedure to measure a and b? In order to answer this question, let's first discuss the right problem or pose the right question. So basically, I have some input variables. So x1 gives me y1, x2 gives me y2, and so on. xi gives me yi, and it goes all the way to yn. Okay? So these are the measured values. But if I give you an a and b, you can also calculate another y, which is ax1 plus b, or ax2 plus b, and so on and so forth. Is everyone with me so far?
Yeah.
So what is the error in the first one? Oops. What is the error in the first one?
y1 minus ax1 plus b.
Excellent. So it's going to be y1 minus a. What does it do there? Okay, y1 minus ax1 plus b. Because the model predicts this much, but the actual measurement is this much. And I can do it for all of them, including the ith one, which is, okay. If I'm very lucky, the A and B that I choose will give me a 0 error here, a 0 error here, and a 0 error in all of them. But I'm not lucky, you know. I mean, or at least I don't count on luck that much. So the error, let's say, let's call this D1 and DI. Is, in general, is D1 or DI positive or negative? Any suggestions?
Might vary, maybe.
Exactly. It could be positive or negative. So basically, we want to choose A and B such that all these DIs are as close to 0 as possible. Okay? But I only have A and B to change, and I could have 100 data points. So then what I define is I can define an error function that I call chi2 to the power of 2, which is sum of I from 0 to n times di's to the power of 2. Can anyone say why I wrote this to the power of 2?
So that sign doesn't matter.
Exactly. I could have, for instance, even wrote it as, I could have written it as absolute value of di. But dealing with this function is very difficult, with absolute function is very difficult, because right at 0, the slope of it is not continuously defined. It's not a continuous function. So that's why we deal with this. So basically, xi squared is sum of I1 to n times yi minus a xi plus b to the power of 2. Oh, I'm sorry. Yeah, this to the power of 2. And all I want to do is I want to minimize this with respect to a and b. So I say derivative of this guy with respect to a has to be equal to the derivative of this guy with respect to b, and it has to be 0. That gives me two functions. These are partial derivatives, two functions with respect to a and b. Okay, so now what I'm going to do is so I'm going to take these to the next page, and I'm going to put them here, and I'm going to calculate the derivatives. Okay, and the calculation of derivatives is extremely simple because the derivative of sum is equal to the sum of the derivatives. Okay, so the first term, this guy, and this is not 2, it's just the derivative, is going to be sum of the derivative of the inside with respect to a. What is the derivative of inside with respect to a? I have this 2, so it's going to be 2 times, I use the chain rule, yi minus axi plus b times the derivative of inside with respect to a. What is the derivative of inside with respect to a?
xi.
Exactly,
Xi.
that's this term. And there's a negative, the xi, right? And there's a negative sign, but I don't care about that negative sign because it's equal to 0. Okay, so now this 2, and there's a summation. So this 2 can go out, I multiply them, so it's going to be 2 times sum of xi yi, this times this, and summation of that, minus this times this is xi squared. A is a constant, comes out of the summation. And b is also a constant, so minus b times xi is 0. Does everyone follow me so far? Yes? Are we good?
Yeah.
Okay, so okay, so now the next thing I want to calculate is the derivative with respect to b. So again, I put it in here. And I want to calculate derivative with respect to b. And derivative with respect to b will be, again, the chain rule, yi minus axi plus b times the derivative of the inside of this guy with respect to b, which is going to be what?
1.
Exactly. Actually, minus 1 because of this sign here, but because it's equal to 0 is 0. This is a little bit trickier than the previous one. This summation will give me some yi. This a times xi, I can factor out a, xi. And this summation of b, what is it going to give me? How many times am I summing b up with itself?
N times.
N times, exactly, because this summation, so minus n times b has to be 0. So then you'll have two equations, This is one of them. And this is the other one. These are two linear equations in terms of A and B, which can easily be solved. And actually, if you look at your lecture notes, this is basically, oops, sorry. A and B can be calculated in terms of these sums. Sxy, Sxx, Sy, Sx. These are the terms that we have here. This is Xx, Sx is here, Xy is here, and so on and so forth. Okay? So that very quickly allows us to calculate the best values for A and B such that this value, this function is minimized. We call this the error function is minimized. Okay? And you can also do a weighted average if the we can exactly do the same things. So basically the only thing here is that I assume the weight of all errors is the same. If the weight of errors is not the same, then you will have a weight function here, and this weight function will just carry into all your calculations. Okay, so that's very simple, and I leave the derivations to you. Now, the goodness of the fit is identified with a parameter here that we call the regression coefficient. The regression coefficient is the difference between the value that the model calculates minus the average value of y, average value of the independent variable, divided by the experimentally measured value minus the average values. Let me see. Guys, some of you said the screen is frozen. Is it working for you?
It's frozen.
Is it frozen for everyone?
Yes.
I believe so.
Oh, wait a second.
I don't see anything.
Wait a second. Wait, I know what's happening. Do you see it now?
Yes.
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 Okay. So now I'm looking at the PDF file of the linear regression. So basically, in the linear regression, we minimize those two errors, and error with respect to A and B. And when we minimize it with respect to A and B, basically we get two linear equations that I just derived for you. You can solve the two linear equations to get A and B in terms of these values. So just look at these values: Sx, which is sum of xi's, Sy, sum of yi's, Sxx, and Sxy. Now, if I go back to my notes, you see that I have them here. And I have them here. Do you guys see it now? Yes?
Yes.
Good.
Yes.
Okay. So now I'm going back to the PDF file of the linear regression, if I find it. Okay. And so far what we did was we minimized this error function, and we assumed that the errors have the same weight. But if we're more interested in certain range of the data, and we want the error in that range to be less, we can give more weight to that range. And all it changes is introduces this weight function. So this weight function will be higher for places where you want to minimize the error. And I leave the derivation of this, how to calculate A and B by calculating the derivative of the error function with respect to A and B to you. It's a very simple derivation. It's again calculating the derivatives with respect to A and B. Okay? Okay. So now, the good news is that we don't need to do all those calculations. Actually, Excel does it for us. So let me share another screen for you. Okay, do you see my Excel sheet that shows a linear relationship between X and Y? Yes?
Yes.
Good, excellent. Okay. So now imagine in an experiment, this column is the value of X that we measured, and this column is the value of this is the independent variable X, this is the dependent variable Y. We changed X and we measured Y. The data is here, and I plotted the data here. These are the data points. Okay? And in order for you to plot the linear, the regression, all you need to do, so I'm going to do it from scratch for you, is you select the data, right click, add trend line. Do you guys see the menu that opened up?
Yeah.
Yes.
Good. You add the trend line. Here you say display equation, display R squared value. And it's here. So this is A, and this is B, and this is the R squared, which is very close to 1. R squared is always between 0 and 1. When it's 1, it means it's perfect fit. When it's 0, it means no correlation between X and Y. So, and that was just one curve. I mean, the first time I encountered this linear fit, like when I was a student, the question I asked myself was, most of the equations we deal with are not linear. So how can this linear regression be really effective in a broader sense? And the answer is that it's actually very effective. I'll give you 2 examples. You see this other tab that I call second order? I just opened it. Do you guys see it?
Yes.
Okay, so let me clear. Okay, so here I again have my X and I again have my Y. So this column is X, this column is Y. And I plotted X or Y as a function of X. And this is the data. And I tried to fit a line to it. It gave me an R square of 0.92 or 93. It's not bad, but when I look at the data, I see that it is clearly showing me a trend. Basically, it's showing me something like this. Basically, if I look at 2 points, like here, oops. If I look at 2 points here, and here, and here, the slope is continuously increasing. This may suggest that I don't have a linear relationship between X and Y. What if I have a second order relationship between X and Y? Y is varying with X to the power of 2. How do I use linear regression to solve this problem, to solve for A and B? Any suggestions? Okay, so the easiest way to do it is to take this as a new variable. Let's call it X prime. I take X squared to be X prime. So now I plot Y as a function of X prime. Basically, here I define another column this data here, which is this x to the power of 2. And I plot y as a function of x squared. So every point here, so let's say, for instance, this point here is this point to the power of 2. There is just one thing. Let me. So basically, this is going to be my x squared, and this is going to be my y squared. Okay, so basically, any point on this axis is the same point here to the power of 2. So now when I plot y as a function of x squared, the slope of, I realize that the y squared is almost, or I realize that r squared is actually 1. So I have a much easier way of saying y scales with x to the power of 2 than y scaling with x. This is a much sounder model. Does everyone follow? So basically, we have linearized this relationship. The relationship by itself is nonlinear because y is a function of a squared, but I write it as y is equal to ax prime plus b, where x prime is actually x squared. Among the examples I gave you today, was there anywhere that we did this linearization? There was one place. Where was it?
When we were plotting lift versus velocity squared.
Exactly. Basically, there we had lift is actually proportional to u to the power of a squared, but then we ended up calling this guy times rho as q. So basically, we were plotting L as a function of u squared, not as a function of u. Okay? So this thing is a common approach that we can do it. Now, we can even go for another function. Let's look at this guy. If I just plot x as a function of y, I get this curve. I get these points. And if I fit a line to it, r squared is very poor, it's 0.55. So I know something is wrong. And actually, when I look at a little bit high x values, I realize that it's very quickly is dropping almost to 0 and remaining 0. This type of drop, almost always, is an indication of somehow an exponential drop, e to the power of minus x, okay? So the type of equation I will be looking for is this, which is highly nonlinear in terms of x. What do? I calculate the natural log of both sides. On the left side, I get natural log of y, and the natural log of product is equal to the sum of the natural logs. So sum of the natural log of this guy and the natural log of this guy. That's the natural log of A, and natural log of this guy is just minus x times b. Because natural log is the inverse of exponential function. So this becomes my new equation. I call this y prime. I call this this is equivalent to my b in the previous calculations, and this is my x. So I plot natural log of y as a function of x. And the slope of this line is what? The slope of this line, minus 0.2. What is this? Is it a? Is it b? What is it?
It's B, right?
Exactly. Because in here, the relationship suggests a linear relationship between ln natural log of y and x with the slope of b or minus b. So minus 0.2 is equal to minus b. The other thing is natural log of a is equal to this. So a is e to the power of 2.30. Okay, so a becomes e to the power of 2.30, whatever this value is. Okay. And so now, if you don't have this data, if you don't want to linearize it this way, Excel gives you another option to linearize. So, for instance, when I right-click on the trend line, I can change the type of trend line. I can say exponential fit, and you see 0.2 and 0.2, and 2.3. Why 2.3? Because a, which is e to the power of 2.3, is this 10. Okay, but what in reality Excel is doing is actually doing this. It's linearizing it this way. Or okay, so and there are other types of linear regressions or nonlinear regressions you can do that is done through linear regression. Bottom line is linear regression is an extremely powerful tool for curve fitting. Okay, so this is what I wanted to cover for today. Next week on Thursday, we will start with a quiz. So the quiz will start sharp at 5 o'clock, and it's going to be a 10-minute quiz. Okay, and the contents is going to be anything and everything that I covered today. Okay, so read the slides, read your notes, and tell me if you have any questions. And so I open the floor to any questions you might have. Questions, comments?
Will the quiz include the different types of experiments?
Yes, yeah, I mean the 3 types.
Yeah.
Yes, yeah, it
Okay.
could, it could, yeah.
Okay.
Okay, thank you guys, and I hope you enjoyed the class, and I'll see you again next week, 5 o'clock, a week from today, 5 o'clock. Thank you guys. Bye.
I have one more question.
Oh, yes, yes.
When was the quiz he was just talking about? When does that happen?
5 o'clock next week.
We're having the quiz next week? Okay.
Yeah.
All right, bye.
Okay, thank you, folks. Bye.
Professor, I had a quick question too.
Yes.
When you started talking about linear regression and you set up that chart with X, Y, A, B, and then you were solving for the error, and you came up with a D1 and like D2, DI, how did you come up with that equation with the Y minus AX plus B? What was that equation coming from for the error?
You mean this one?
It's just showing your face right now. I can't see your screen.
Oh, wait a second. Where did it go? Okay. You mean this equation, or this is, let me just fix this.
I think it was on the previous slide.
Was it in the previous slide? You mean this?
Yes, in the top right corner, the y1 minus ax1 plus b equals d. What does that represent?
So this is what the model will predict for y1. This is what the experiment gave us. So the difference between them is our error.
Okay. All right. Thank you. That makes sense.
Questions, folks?
Would the new slides with all the new work that you added on be uploaded to eCampus or?
No,
we
no,
have
no,
to
no,
s-
no.
Okay.
These are your notes. Yes.
Okay.
Okay, thank you guys. And see you next week.